In this example, we're going to use a change of variables to evaluate each integral. The substitution rule gives us a method for integrating using the change of variables. Following the procedure indicated here, we will need within our integrand to be able to identify a composite function, and that composite function will have an inner function that we'll identify as u. And we must do this in such a way that we also observe within the integrand, attached through multiplication, a constant multiple of the derivative of u with respect to x. If we are able to do this, then we can proceed with the process. Now, not all integrals yield to the substitution rule as is indicated here, and it is also the case that there are variations on the substitution method. But all of the examples that are going to be presented in this video are going to lend themselves to this procedure, and we will use this specific procedure to integrate for all of the examples that are about to be presented. So here's our first example. It's the indefinite integral of 4x cubed divided by the square root of 5 plus x to the fourth dx. Let's rewrite this. We will rewrite it as the indefinite integral of 5 plus x to the fourth quantity raised to the negative 1/2 power times 4x cubed dx. So now we need to select the composite function within the integrand. A reasonable choice could be the first piece of the integrand, namely the 5 plus x to the fourth to the negative 1/2 power. Certainly looks like a composite function, and if this is the case, then u, the inner function, would be the 5 plus x to the fourth. Let's try that. So let's let u be 5 plus x to the fourth, and if this is the correct selection, we're rewriting the first part of the integrand as u to the negative 1/2 power. But now, to confirm we've made the proper selection, we have to differentiate u with respect to x. So we need to calculate du dx. And du dx, the derivative of u with respect to x, is 4x cubed, coming from the derivative of x to the fourth being 4x cubed. But now, for the purposes of integration by substitution, we want to write all of our derivative equations in differential form, meaning that we want to move the dx to the other side of the equation. So in that form, du is equal to 4x cubed dx. So now as we have this derivative written in differential form, we need to see if our integrand contains this du expression or contains a constant multiple of du. So looking back to our integrand, we do see exactly du. We see 4x cubed dx. So that means our selection of the composite function and identification of u is proper. And now we can rewrite our integrand, or our integral, I should say, as the integral of u to the negative 1/2 du. So now that we have rewritten our integral in terms of u, now we can evaluate it. Applying the power rule, the antiderivative of u to the negative 1/2 is 2u to the 1/2 plus c. Now that we have our antiderivative function, we rewrite it in terms of x. So we go back to our selection of u. Our identification of u was that it was equal to 5 plus x to the fourth. So now our final result in terms of x is 2 times 5 plus x to the fourth quantity to the 1/2 power plus c. So this is our finding. We have evaluated this indefinite integral using the substitution method as detailed on the previous slide, and this was our result. But since this is a new process, let's check our result. If we're going to check our result, we'll do it by differentiation, and when we differentiate our result, if we have done this correctly, we should get back our original integrand. Now, as we look to differentiate 2 times quantity 5 plus x to the fourth to the 1/2 power with respect to x, we can see that that differentiation is going to involve the chain rule. So differentiating the outer function means that the 1/2 power is going to come down front and get multiplied with the 2, and then the exponent's going to decrease by 1. So our derivative will be 5 plus x to the 4th to the negative 1/2 power, but then we multiply by the derivative of the inner function, so times 4x cubed. And this derivative is exactly equal to our original integrand, so our work checks. There's a direct link that we can see established here between the process of integration by substitution and differentiation using the chain rule. Whenever you check a result that you've gotten using integration by substitution, the check is always going to involve the application of the chain rule. And it's always a good idea to check your results. Let's move to our second example. Our second example is the indefinite integral of sine squared of 6x times cosine of 6x dx. Again, let's rewrite this just for clarification. Sine squared of 6x, remember, is the sine of 6x quantity squared times cosine of 6x dx. So now let's look for a composite function within our integrand, and there is a composite function candidate right here. The sine of 6x quantity squared could be our composite function. Let's let u be the inner function. So u is going to be the sine of 6x. And if that's the correct choice, then the first part of our integrand will get rewritten as u squared. But now we have to differentiate u with respect to x in order to determine that we've made the correct choice. So the derivative of u with respect to x in differential form is going to be du equals the cosine of 6x times 6 times dx. Again, that's in differential form, which can be rewritten as 6 cosine of 6x dx. So now if we look to our integrand, the piece that remains isn't exactly du, but it is a multiple of du. Specifically, cosine of 6x dx is 1/6 of du. So this confirms we've made the correct selection of the composite function and identification of u. And now we can go ahead and rewrite the integral in terms of u. When we do this, it's going to be the integral of u squared times 1/6 du. And through the properties of integration, we know that we can bring the 1/6 coefficient out front and have the integral of u squared du. And now we can go ahead and evaluate this integral. Applying the power rule to the u squared, our result is going to be u to the 3rd over 18 plus c. So now that we have evaluated our integral, it's time to substitute back the x expression. So our final result is going to be sine cubed of 6x over 18 plus c. Our third example is the integral of 9x squared over x cubed minus 7 dx. Let's rewrite it. We can rewrite this as the integral of x cubed minus 7 to the negative 1 power times 9x squared dx. In that format, let's again look for a composite function. It appears that our x cubed minus 7 to the negative 1 power would be a candidate, and the inner function there would be x cubed minus 7. So we'll let u be equal to x cubed minus 7. With that selection, the first part of our integrand will get rewritten as u to the negative 1 power. But again, we must differentiate u with respect to x to determine that we've made the correct choice. So again, our derivative of u with respect to x in differential form is going to be du equals 3x squared dx. So now if we look to our integrand, we have 9x squared dx. It's not exactly du, but it's a constant multiple of du. In fact, it's 3 du, so that means, again, our choice is correct and we can proceed with our process. So now we will rewrite our integral in terms of u. it will be the integral of u to the negative 1 times 3 du. Once again, the 3 can be brought out front, and we'll have the integral of u to the negative 1 du. So now to evaluate this integral, remember, this looks like a power function, but remember that the negative 1 power does not yield to the power rule for integrals. Instead, the antiderivative of u to the negative 1 power is the ln of the absolute value of u. So our result here is going to be 3 times ln of absolute value of u plus c. Finally, we'll substitute back our x expression, and our result then is 3 times ln of absolute value of x cubed minus 7 plus c.